In this video, we will be talking about the properties of alkanes. As with everything, you choose what it's going to be used for based on the properties it has. So for example, alkanes that are solid at room temperature are typically used as waxes or lubricants. Liquid alkanes are generally used as fuel or solvents, and alkanes that are gases at room temperature are typically used as fuel. So examples include paraffin wax for burning candles, and then gasoline and hexane and natural gas for fuel. So the state of matter at room temperature entirely depends on the intermolecular forces between the molecules. So if you have really strong intermolecular forces between your particles, you can be a solid at room temperature. We can think of this as a number line where you have your boiling point separating your liquid from your gas, and then your melting point separates your solid from your liquid. The main question is, where is room temperature? So if you're a liquid at room temperature, then room temperature is between the melting point and the boiling point. If the substance is a gas at room temperature, then room temperature is here, above the boiling point. And if it's a solid at room temperature, then room temperature is below the melting point. When we melt or boil a substance, what we're doing is we're breaking the intermolecular forces shown as dotted lines between these particles. Once those intermolecular forces are broken, then the molecules are free to move past one another, but there's still some intermolecular forces of attraction between them. If we separate the intermolecular forces again, we can turn that substance into a gas. So we have to differentiate between chemical bonds, which are very strong, and intermolecular forces, which are very weak. So when we draw our line structures, we are drawing the covalent bonds that hold our substance together. Those covalent bonds are what define our compound. And so when we boil or melt a substance, we are not breaking the covalent bonds. We are only severing the intermolecular forces. Intermolecular forces literally mean between the molecules. So between two molecules is an intermolecular force of attraction that is much weaker than ionic or covalent bonds. Much, much weaker. So we are going to be focusing on these three intermolecular forces, which are all much easier to break than a covalent bond. Hydrogen bonds are the strongest intermolecular force. Dipole-dipole forces are the middle ground, and then London dispersion forces are the weakest. We'll start with London dispersion forces. If we draw a nucleus here, then the electrons are always moving around the nucleus of our atom. The electrons are constantly in motion. So if at one point in time, all of the electrons end up on one side of the atom, then that side of the atom is going to be partially negative. And the other part of the atom is going to be partially positive because the nucleus is exposed. And so that's exactly what's happened in this figure. All of the electrons just shifted to one side temporarily. Since the electrons are always in motion, they will move back to one of the other more neutral states in a little microsecond, picosecond, very short time frame. But for this instance that they are all on one side of the molecule, then that's a temporary dipole. We call it a dipole because di means two and pole means like positive and negative. This little delta here means partial. That means it's more than 0, but less than 1. So somewhere in between 0 and 1. So 1 would be fully positive charge, and then 0 is not charged at all. So delta just means partially charged. So if this part of the atom's partially negative, this side's partially positive, and then a nearby atom exceeds that positive charge, and so its electrons get moved over. And this is an induced dipole, because it was only experiencing this dipole because this one wasn't a dipole. And that can cause an additional shift with these electrons shifting over to be near that positive charge, exposing this side to become a positive charge, which makes those electrons in that atom attracted. And so these weak attractions between molecules are our dispersion forces. So all that yellow glowy stuff in the figure is a dispersion force. There are some trends for chain length and dispersion forces. Since dispersion forces are entirely dependent on how many electrons are in your molecule, the more electrons you have, the more dispersion forces you're going to have. So if you have longer chains, you've just increased the probability that some of these electrons are going to shift to one side of the molecule. And so if you have a longer chain, then you're more likely to have dispersion forces. You can see here in this table that as the number of carbons increases in the molecule, then the boiling point becomes closer to 0. And so this is an increasing boiling point. So larger molecules, more dispersion forces, higher boiling point. And we can use molar mass as a shortcut for figuring out our relative size of the molecule. So if it has a very large molar mass, then that means that there's more atoms there than if it has a low molar mass. Additionally, there are trends for the degree of branching in a molecule. This is akin to Pringles potato chips versus Lay's potato chips. If you have straight chain molecules, then they are able to pack together much more closely than if you have a branched shape. Try and draw crazy branched molecules. So that molecule there and this molecule here, they just can't pack together very well. And so branched molecules will have fewer dispersion forces because they're just not close to one another. And so straight chain molecules will have more dispersion forces. I'm going to write branched there, and that's straight. So if we have more dispersion forces in the straight chain, then that means that it's going to have the higher melting point and boiling point. Our next intermolecular force that we're going to talk about are dipole-dipole forces. Unlike our dispersion forces, which are between temporary dipoles, dipole-dipole forces here are between permanently polar molecules. And so each molecule here has a permanent dipole to it. And so this is formaldehyde. The oxygen here is more electronegative than the carbon. And that means it's going to pull all the electrons towards it. So it's pulling electrons towards it. And that's going to make the oxygen more negative and the carbon more positive. Since this dipole is permanent, it always is there, then another molecule, just like it, is also polar. Opposites attract, and so you'll have the partially positive end of one molecule align with the partial negative of another molecule. And so this dotted line here is representing the dipole-dipole force. That dipole-dipole force is called dipole-dipole because it requires two dipoles. So it's between one dipole and a second dipole. This is also an example of a dipole-dipole force in this dotted line here between hydrochloric acid and another molecule of hydrochloric acid. Both of these have a dipole, and then that is between the two ends. Hydrogen bonding is our strongest intermolecular force. Hydrogen bonding involves it's like an extreme dipole-dipole. It can only occur between what we call a donor and an acceptor. So if we look at the chemical structure of water, water is a classic example of where hydrogen bonding can occur. We are going to need to have a lone pair on a nitrogen, oxygen, or fluorine, such as that one. And so that's going to be our acceptor to take on a hydrogen bond from another molecule. On another molecule of water, we need to find a donor, which means a hydrogen that's covalently bonded to a nitrogen, oxygen, or fluorine, a NOF. NOF is NOF. And so this is our donor. And so a hydrogen bond forms between there. This happens because the oxygen is so electronegative, it's pulling electrons towards it, making the hydrogen extremely partially positive. And this oxygen just can't get enough, and so it's trying to pull that hydrogen as well. This slide summarizes the requirements to have all of these different intermolecular forces. Dispersion forces occur between all molecules. Everything has dispersion forces. For dipole-dipole, you need to be a permanently polar molecule. You can help decide if your molecule is polar by looking at the electronegativity differences. Carbon and oxygen, carbon and nitrogen, carbon and fluorine, and carbon and chlorine all have polar covalent bonds. Then carbon and hydrogen has a non-polar covalent bond. So if you have only carbon and hydrogen in your molecule, you're going to be a non-polar molecule. If you do have polar covalent bonds, they need to be arranged in an asymmetrical manner so that they do not cancel out. So for instance, carbon dioxide has equal and opposite polar covalent bonds, and so this direction completely cancels out with that direction in the tug of war, and so it's non-polar overall because it's symmetric. So you need polar covalent bonds and you need to be asymmetrical to be polar. For hydrogen bonding, you need to have a donor molecule which has a lone pair. No, donor is the hydrogen bonded to a nitrogen, oxygen, or fluorine, and then an acceptor is the lone pair on a nitrogen, oxygen, or fluorine. Now I want you to make a prediction. Which will have the higher boiling point and why? 2,2-dimethylpropane, or water? Make a claim and provide evidence and reasoning for your answer. Pause the video and then unpause the video when you're ready to check your work. Okay, water will have the higher boiling point. Water is going to have the higher boiling point because it is capable of hydrogen bonding. Two,2-methylpropane looks like this. 1, 2, 3, 2,2-dimethyl. And so it's going to be branched. It's going to have only carbon and hydrogen, which makes it nonpolar. Since it's nonpolar, it's dispersion forces only. Technically, since this one has hydrogen bonding, it also has dipole-dipole and dispersion. But since hydrogen bonding is the strongest, then that's going to really trump the decision here. So that's the strongest intermolecular force. And so it'll require the most energy to break. And so it's going to have the highest boiling point. For solubility, we need to consider this rule of thumb that is like dissolves like. And that means that like means intermolecular forces. It doesn't mean similar elements. It means similar intermolecular forces. Polar solutes will dissolve in polar solvents. Solvents do the dissolving. Solute is what's dissolved. What is dissolved? And a solvent, which does the dissolving. So that's the major component here. So polar dissolves in polar. Non-polar would dissolve in non-polar. But a non-polar solute will not dissolve in a polar solvent. And so, similarly, if we had a polar solute in a non-polar solvent, that would also not dissolve. So we have to have either polar with polar or non-polar with non-polar in order to make that dissolve. And those are not attracted to one another because if it's polar, then the polar solvent molecules are going to be more strongly attracted to other solvent molecules than they are to the solute. In order to dissolve, the solute needs to be similarly attracted to the solvent molecules like the solvent molecules are attracted to themselves. That way it can squeeze its way in and be part of the mix. Let's make a prediction. Would glucose, which has the chemical structure shown below, be soluble in water? Your answer should include a claim, which directly answers the question, evidence, which means what did you observe that led you to make that claim, and you should include reasoning that shows how the evidence supports the claim. Go ahead and pause the video and try to come up with this, and then you can compare to me when you unpause the video. Okay, so I'm going to answer this claim by directly answering the question. I'm going to say glucose would be soluble in water. Where I can write glucose is soluble in water. Glucose is soluble in water because it is polar due to the OH groups. And aldehyde. And then this evidence needs to show how this statement supports this claim that it's going to be soluble. And so water is a polar solvent. Glucose can hydrogen bond to water and since they are both polar, then due to that rule, like dissolves like, they will be soluble. But since glucose can hydrogen bond to water, that will make it more soluble than just an ordinary polar solvent. So I don't have a lot of room to write in here, but I'm going to just quickly write like dissolves like, and that they're both polar. But I don't want you to just say they have similar intermolecular forces. I do want to see specifically what intermolecular forces are possible within the substance. So if you could squeeze in that like they're both capable of hydrogen bonding to one another, that would be awesome. I just didn't have a lot of room to write.